For the longest time, the world of location tech has been obsessed with one thing, and that's precision. But what if getting someone to the right 3-meter square is really only half the battle? Today, we're going to talk about the next giant leap, building a semantic Earth, a world where any coordinate doesn't just tell you where you are, but it instantly and automatically tells you exactly what is there.
So how do we actually get there? Well, first, we're going to start by really unpacking the core problem, what we're calling the blind coordinate. Then, we'll dive into the AI toolbox that lets machines actually see the world. After that, we'll look at the planetary scale filing system we need to make it all lightning fast. And finally, we'll see how we can bring it all together into one powerful, context-aware engine.
So, at its heart, the fundamental challenge we're tackling is this critical gap. We've built these incredible systems that can pinpoint a location with unbelievable accuracy, but there's a huge disconnect when it comes to truly describing what's at that position.
Okay, let's be real. Your team at What 3 Words has absolutely nailed the where problem for the entire planet. Anyone can name a precise 3-meter square, which is just incredible. But that achievement naturally brings up the next big question, especially for the folks out in the field. Beyond the address, what is that square actually made of?
This is what researchers are calling the coordinate context paradox. We have this pinpoint accuracy on position, but it's completely disconnected from the rich context of that spot. Is it a paved road or a muddy field? Is it public property or is it private? A sheer cliff face or a gentle slope? Right now, the coordinate itself has no idea.
And this paradox isn't just some academic idea. It creates a real, tangible, and often dangerous delay. I mean, think about it. For a 911 dispatcher or a logistics coordinator, every single time they get a coordinate, a clock starts ticking. It takes them, on average, 2 to 5 minutes of this frantic manual research, pasting coordinates into different map layers, visually scanning satellite photos, just to figure out the ground truth of a single spot.
And that delay, it translates into some serious real-world costs. For emergency response, it means sending a standard ambulance when an all-terrain vehicle is what's really needed, sometimes doubling response times. In logistics, it's that truck that gets stuck in the mud, leading to a failed delivery and wasted time. And for the human operator at the center of it all, it's a massive cognitive load, forcing them to make these high-stakes decisions with incomplete information.
Okay, so how do we even start to solve this? Well, the foundation is the technology. Specifically, it's about teaching machines to perceive and interpret the physical world using AI, kind of like a human would, but doing it at a global scale.
This table gives a really great overview of the AI toolbox we have to work with. Basically, we can use different AI models to look at different kinds of data. So one model can analyze satellite imagery to tell us if the ground is mud or ice. Another one can look at 3D elevation data to calculate the exact slope of a hill. And then there are these cutting-edge deep learning models that can look at an aerial photo and label every single pixel. This is road, this is grass, this is a building, creating this incredibly rich, machine-readable map of reality. And here's the crucial takeaway. This is where it gets really powerful. We're moving beyond a simple static map that just says, this is a field. We're building a predictive, dynamic system. A system that can take in the specific model of an ambulance, combine it with real-time weather data, and tell a dispatcher the precise probability that their vehicle will get stuck. That's not just a map anymore. That's a decision-making partner.
But look, generating all this rich data is only half the battle. If it takes 5 minutes to run the analysis for a single point, we haven't solved the core problem, right? We're still stuck with that delay. We need answers in milliseconds, and for that, you can't just use a standard database. You need a specialized indexing system for the entire planet, and that is where Discrete Global Grid Systems, or DGGS, come in.
For all the engineers in the audience, this slide highlights a classic and really fascinating architectural choice. On one side, you've got Google's S2, which uses squares. It's incredibly efficient for storing data and asking questions like, hey, is this point inside this region? But on the other side, you have Uber's H3, which uses hexagons. Now, this is topologically way better for analyzing movement and flow since every neighbor is the exact same distance away. The choice isn't just technical, it fundamentally defines what kinds of questions your system can answer the fastest. And get this powerful indexing idea doesn't stop at the ground. By extending the grid upwards into a 3D voxel system, we can map airspace with the exact same efficiency. This is the foundational tech that makes near-instant collision checking for drone delivery fleets and urban air mobility possible. It turns a ridiculously complex computational problem into a simple, scalable lookup. Okay, so we have the raw data from our AI tools, and we have it all organized in a super fast index.
The final piece of the puzzle is the intelligence layer, the brain, right? The part that can orchestrate all these different components to produce a single smart decision.
That's where something called a geospatial knowledge graph comes into play. It's not just a database, it's a network of relationships. It lets a system connect all these different facts, like this location has clay soil, it just rained 2 inches yesterday, and it's in a historical flood zone. By following those links, the system can infer a brand new, emergent risk, like soil liquefaction, that wasn't explicitly stated in any single data source. It's all about discovering the unknown unknowns.
This workflow is a perfect example of how a modern LLM can act as the mission commander for this whole process. You give an AI agent a high-level goal, something like assess this site for a temporary field hospital. And then it just goes to work all by itself. It queries the indexed terrain databases, it invokes the visual AI tools to check the latest satellite imagery for access roads, and then it synthesizes all of those findings into a simple, coherent report for a human to review. It's amazing.
So let's bring all these incredible components together. What does the final integrated solution, this context-aware engine, actually look like when we put it all together?
A reference architecture for this engine would process a query in a really logical flow. A request comes in through an input gateway, which can handle any location format you throw at it. The indexing core instantly finds all the pre-computed data for that spot in what we call the attribute fabric. If needed, the visual inference engine can analyze new imagery on the fly. And finally, the synthesis agent acts as the storyteller, weaving all that data into a clear, actionable recommendation.
Let's make this really concrete. Here's the before state for an emergency call. A 911 dispatcher gets a coordinate. On their screen, it's just a blinking red dot on a basically blank map, and the clock is ticking as they frantically try to figure out what is at that dot.
Now here's the after. The exact same coordinate hits the system. But in under a second, the context engine has already analyzed the terrain, the soil, the recent weather. The dispatcher doesn't see a dot. They see a clear, life-saving recommendation. High risk of vehicle immobilization. Deploy the 4x4 unit. That research delay is just gone. Completely eliminated.
And it's the exact same story in logistics, and it's playing out thousands of times a day. A coordinator dispatches a full-sized 18-wheeler to a new commercial address, totally blind to the site's physical constraints. The truck shows up, can't make the turn into a tight loading dock, and the entire delivery becomes this costly, time-wasting failure.
But with the context engine, that failure is prevented before it even happens. Before the truck is even assigned, the system uses visual AI to identify the loading dock, it analyzes the geometry of the lot, and it even pulls local curb data to find delivery windows. It provides specific, actionable intelligence that guarantees the right vehicle is sent the first time.
So we'll end with this question for you. Because solving the what behind the where is so much more than just an optimization, it's the foundation for a whole new platform. When every single addressable point on the planet can instantly describe its own physical reality, well, it unlocks a new universe of applications. For autonomous vehicles, for smarter insurance, for resilient urban planning, and for countless ideas we haven't even imagined yet. The era of the blind coordinate is over. The semantic Earth is next.